The pre-predator model is a model to simulate the population growth of two species are in a relationship of predation, like wolves and sheep. This model helps ecologists to study the factors regulating the population in a food chain, and it is a good example of mathematical logic and technique applied into other scientific areas.
The growth rate of prey is expressed as dx over dt equals to ax minus bxy, and the growth rate of predator is expressed as dy over dt equals to cxy minus dy. And we'll assume x is the number of prey, y is the number of predators in both functions over time. The establishment of the pre-predator model belongs to two mathematicians, Alfred J. Lotka and Lotka-volterra. Lotka concluded this relationship while he was on the research of physical chemistry in 1925 in the US. As the Italian scholar Lotka-volterra also had the similar discovery while he was developing the work of the logistic growth model in 1926 independently. Therefore, this model is also known as the lotka-volterra model.
To make the simulation, the model has to satisfy the following assumptions. Number 1, the prey population finds ample food at all times, so the prey side always have food to eat.
Number 2, the food supply of the predator population depends entirely on the size of the prey population. Number 3, rate of change is proportional to its size. This is also the most important assumption in our model. This principle is based on the exponential growth of the logistic growth model. dn over dt equals to r times n, where n is the population and r is a constant.
Number 4, predators have limitless appetite. This means that the predators always want to eat the prey in our simulation. Number 5, the environment does not favor any side of species.
The assumption 2 and 3 make sense that there are interactions in both equations, because the predators will eat the prey, so that in the prey function, the amount eaten by the predators reduces the growth in prey, and this is up to the likelihood of how much the prey and the predators met.
As well as in the predator function, only the amount of predators who have food to feed on will survive, and this is corresponding to a distinct coefficient C. The reason why C differs than B is that, for example, a sheep is eaten by the wolves means a decrease in the population of sheep, but does not equal to an increase in the population of wolves.
We can solve the equation by separation of variables. cxy minus dy dx equals to ax minus bxy dy, and perform integration on both sides.
Set the two equations to 0. The critical values are x equals to 0, y equals to 0, and x equals to d over c, y equals to a over b. Next, we can do the Jacobian matrix by taking the partial derivative of each function. Take the first fixed point 0, 0, we get a saddle point, means as time goes by, x and y will not approach 0. Then, we take the values where y equals to a over b and x equals to d over c. By doing the calculation, we get another matrix. This is almost elliptical, and this is what we want to see how their population relationships fluctuate.
In an initial state, we rationally assume that there is more prey and less predators, and this leaves out the room for prey to grow. Like, when there is not a lot of wolves to eat the sheep will grow fast. During this period of time, the predators have sufficient food supply, so they start to rise in quantities by eating the prey. As time passes, it will reach a point of max value of predators, then start to fall due to the lack of food. As a result, there is a period. Both prey and predators have a hard time in quantities. The less predators provide a gap for prey to grow. Then, the new cycle starts.
In our model, we come up with a general idea of how the populations of prey and predators change over time, as well as we show it into the graph to see the motion moving in the rate of change.